Every time a spacecraft tears through the atmosphere or a terabyte of data flashes across the globe in a millisecond, it is obeying an invisible, ancient set of rules. For thousands of years, humanity was at the mercy of the elements. We couldn't predict the weather, or even harness energy, or travel faster than a horse, specifically because we couldn't read the physical laws governing our environment. Overcoming those natural limits required a multi-generational pipeline of human ingenuity. First came the theorists, who decoded the mathematical language of reality. Then came the engineers, who took those equations and built actual machines. The study of basic physics bridges that gap, providing the blueprints to build atop nature rather than merely reacting to it. The era of decoding began by mapping how objects moved. Galileo determined the exact rate at which bodies fall to Earth, while Johannes Kepler calculated the precise elliptical orbits of the planets. These were the first victories over the unknown. Sir Isaac Newton took those isolated observations and linked them together. He proved that the same force pulling an apple to the ground is what keeps the moon tethered to the Earth, unifying the cosmos under one universal law of gravitation. This animated cross-section demonstrates the principles of fluid dynamics. Daniel Bernoulli calculated how fluid speed directly creates changes in pressure. Bernoulli's theorem dictates the exact ratios of lift and drag required for heavier-than-air flight, enabling commercial aviation. By the 19th century, physics ventured into forces the human eye couldn't see. James Clerk Maxwell wrote the classical theory of electromagnetic radiation, proving that electricity, magnetism, and light are all manifestations of the same physical phenomenon. Then Albert Einstein redefined our core concepts of time, space, and gravity. His theory of relativity and the equation E equals mc squared proved mass and energy are interchangeable quantities. This scientific awakening extended even to the life sciences. While physicists mapped the stars, Charles Darwin decoded the biological rules of existence, proving that the natural world followed a logical, detectable system. These theorists wrote the instruction manual for the universe. An equation on a chalkboard cannot light a home or power a city on its own. The search for the universe's limits turned completely inward. Physicists moved from tracking entire planets to hunting for the microscopic, unseen building blocks of matter. Marie Curie pioneered the research into this space. She coined the term radioactivity, and her work proved that atoms were not solid, indivisible blocks, but dynamic structures constantly shedding energy. Building on that foundation, James Chadwick discovered the neutron. Identifying this neutral particle gave scientists the ability to manipulate the nucleus of the atom itself. Mapping the subatomic realm bridged pure theory and applied mechanics. It gave humans the ability to manipulate the very fabric of reality to generate power. The era of applied science accelerated with Michael Faraday's discovery of electromagnetic induction, demonstrating how a moving magnetic field can generate an electric current. Engineers quickly put Faraday's principles to work. Nikola Tesla and Thomas Edison used these discoveries to construct the alternating current electrical systems that serve as the foundation for modern power grids. Edison's electric light bulb demonstrated that abstract physics could be physically manufactured to illuminate the dark. By the mid-20th century, inventors John Bardeen and William Shockley applied quantum mechanics to build the transistor. This single component allowed engineers to shrink room-sized machines down to modern microelectronics. Modern nations applied these rules to advance their societies. Here, Dr. C.V. Raman won a Nobel Prize for discovering how light scatters through a transparent liquid. This chalkboard maps the exact spectral signatures, proving how specific molecular structures manipulate light waves in real time. This physical understanding sparked an explosion of applied fields across India. Jagdish Chandra Bose invented the crescograph to physically measure plant growth, while Dr. Prafulla Chandra Ray synthesized mercurous nitride, advancing applied chemistry. Dr. Homi J. Bhabha took the subatomic theories established by scientists like Curie and Chadwick and applied them directly to national energy sovereignty, becoming the father of the Indian nuclear program. And Dr. A.P.J. Abdul Kalam engineered fluid dynamics, material science, and propulsion equations to develop advanced missile and space launch vehicle technology. These inventors, chemists, and engineers are the world builders. They took the theoretical rulebook written over centuries and physically forged it into the scaffolding of modern civilization. Look at the world around you right now. Behind the glass screens, the concrete highways, and the cellular networks, there is a hidden layer of mathematical theory supporting every structure. Look closely at a space launch. You are watching Newton's gravity, Bernoulli's fluid dynamics, and Coulomb's aerospace engineering igniting in unison. The equations taught in basic physics function as the living source code of human innovation, remaining as relevant in a high-tech lab as they were on a 19th century chalkboard. To invent the technologies of tomorrow, we must first master the fundamental laws of the physical universe today.
Thank you for exploring the universe with us. Subscribe to Fundamental Physics for more.